Topographic Office of Land Information in New Zealand, and he's a member of the New Zealand Institute of Science and Surveyors. Graeme obtained his Bachelor of Surveying from Otago University in 1980. He worked then for the New Zealand Geological Survey, which is now GNSS Science, in their Earth deformation section, using geodetic techniques to measure, monitor, and study crustal deformation across New Zealand. Good place to measure it. In 1992 and 93, he worked for University Navstar Consortium here in Boulder, working with scientists using GPS to measure plate tectonics in Turkey, the South Pacific, and the U.S. In 95, he moved to Land Information New Zealand, where he worked for the Office of Surveyor General before moving to his current position as Chief Geodesist for the National Geodetic Office, where he continues to work on the development and implementation of the geodetic system in New Zealand. He is also manager for the National Topographic Office, addressing group and business development groups within LINS. Graeme is currently the New Zealand chair for the FIG Commission 5.2 on reference frames and geodesy examiner for the New Zealand Institute of Surveyors Admissions Panel. So please join me in welcoming Graeme.
All right. Thanks, Megan. Well, it's great to be back. It's always good to come back to Boulder. I was just chatting before. It's nearly over 20 years ago now that we spent 2 years in Boulder, and in some respects Boulder seems like a bit of a second home. And every time, hey Jim, good to see a face here. And my wife and whenever we come back, we always feel very fondly of Boulder and the time that we had here in the States. It's really interesting to see a lot of new faces, but it's also nice to see some old faces from the time that I was here back in the early 90s. So today what I'm going to talk about is a little bit about Land Information New Zealand, some of the geodetic programs, some of the work we're doing, and then hopefully we'll have a bit of time. I'm going to spend the second half of the presentation talking about some of the geodetic aspects and the work that we've done in Canterbury following a series of large earthquakes that occurred about 3 years ago, which caused a lot of widespread damage and disruption, and also the geodetic infrastructure and the surveying that was done following the earthquake, and it's still going on down there as they start rebuilding Canterbury, was extremely important because it has presented some really quite unique problems from an agency that manages the geodetic framework within New Zealand. It also had a lot of use, of course, from a scientific perspective, in actually determining what some of the mechanisms were for for the earthquakes that occurred. So this is going to work. Just a second ago. Spacebar. There we go. Right. Okay. So just a little bit about LINS. So Land Information New Zealand is the national survey and mapping organisation in New Zealand. Has a number of parts to it, and we're just going through quite a major refocusing and restructuring within our departments. We have three outcome areas. One is secure property rights. So LINS administers and manages the national title and cadastral surveying system within New Zealand. So any property transactions, cadastral surveys are managed and sort of, I guess, probably the most major function. We also are the managers of Crown land in New Zealand. So LINS administers the largest holding of land within New Zealand, Crown land, which is a sizable portion of New Zealand. And if any overseas investors want to purchase property in New Zealand, then it's up to LINS to go through a process to see if they're worthy people to purchase the land, that they're going to use it to the best advantages for New Zealand. And then the third area, which is an area which is being looked at very closely at present, is an area we call location-based information. And within this area here come a number of different activities that LINS administers. So one of the core functions of this group is the management of our Geodetic Framework, so the National Geodetic Office, so I'm responsible for that group. We also have our National Hydrographic Office, so hydrography, providing charts, electronic navigation charts is administered and carried out under a function of LINS. We have our National Topographic Office, which administers or provides topographic mapping throughout New Zealand. It's a function in an area that I also am responsible for. We look after addressing in New Zealand for a number of purposes, addressing for electoral purposes, for postal purposes, and for emergency services. We also have a new group which we're calling Business Development, which looks after or is responsible for coordinating the capture of aerial photography and satellite imagery across New Zealand. What have I missed out there? So there are quite a number of diverse functions within land information in New Zealand. And of course, the Geodetic Framework is the core function that enables all those diverse data sets to be brought together. So I'm going to focus the first half of this presentation looking at what are some of the functions of that group, what are some of the initiatives that we're currently working on. A little bit about the tectonics of New Zealand. So here we are down here in the bottom of the South Pacific. So unlike Australia, New Zealand sits across a plate boundary, similar to Japan, and I guess California here in the US. So half of New Zealand is tied to or is part of the Pacific plate, moving in a north-westerly direction. Part of us sits on the Australian plate and is moving in a northwesterly direction. So across New Zealand, we have a lot of deformation occurring, and that gives rise to, I guess, a very active geological environment. Certainly plenty of historic earthquakes. We have an area of back arc spreading up in the North Island. And back in the early 90s, how I became first involved with UNAVCO was a project that Chuck led down in New Zealand, looking at deformation across the Taupo volcanic zone. So from a geological perspective, a lot of interest in New Zealand, and of course, using geodetic surveying techniques plays a key role in trying to understand some of those mechanisms. But from LINZ's perspective, we have to provide the spatial framework for cadastral surveying, for all surveying in New Zealand. And one of the challenges for us is that how do we build in these dynamics to accommodate the fact that New Zealand is moving in quite an unusual fashion, and we also have to accommodate these effects of large earthquakes. So in New Zealand, the geodetic framework is the underpinning spatial framework for all these different spatial layers. And our aim with our geodetic network is to have a spatial framework that is accurate across New Zealand with an accuracy of about plus or minus 5 centimetres. Now, if New Zealand is moving differentially by anything up to 6 or 7 centimetres a year, irrespective of the fact that we have large earthquakes, it presents us a problem, because if we have this nice, tight geodetic framework, and we want to maintain that spatial accuracy of about 5 centimetres, it means that after a year, the datum goes out of date. So we've looked at some, I think, well, were certainly at the time when we developed our new datum, some quite innovative approaches as to how we're going to manage that from a practical perspective. So back in early 2000, LINZ decided to implement a new national datum. We called it New Zealand Geodetic Datum 2000, and it has a reference epoch of the 1st of January 2000. So you could say that as of the 1st of January 2000, all the coordinates in that datum were spatially referenced, and they were correct at that date. But of course, since then, we've had these effects of deformation that's occurring. Two diagrams on the bottom left there show the shear and the shear rates, shear strain, and the aerial strain rates across New Zealand. So what we chose to do to keep the accuracy was to define a deformation model for New Zealand that modelled the plate tectonic movements across New Zealand, and we implemented that as part of the national datum, so that when we make measurements today with our GPS or traditional surveying, we can take those measurements, we can apply this deformation model, and then migrate those observations back, if you like, correct them, to the reference epoch of the datum of 2000.0. So our national datum has a deformation model that's part of it. We were the first country in the world to have a working datum that incorporates the deformation model. But interestingly now, countries like Japan, parts of Asia, which also sit across plate boundaries, are implementing these national datums with these deformation models built into them. Just some details of the datum. A new datum had a geocentric origin. It was tied to ITRF 96, and as I said, we call it a semi-dynamic datum. So it's not dynamic in the sense that the coordinates of all our cadastral boundaries and geodetic control points are actually moving, but we're actually migrating the observations back to how they would have been at 2000.0. Now that's relatively straightforward to accommodate the effects of plate tectonics, but when you have a large earthquake, it presents some quite unique problems, and I'll talk about that shortly. So our traditional geodetic network, going back historically, was made up of traditional survey observations, many trig stations around the country, about 120,000 geodetic survey marks, all with accurate coordinates on them. But of course, over the last 20 odd years, there's been a transition away from the more traditional survey marks on the ground to the greater use of GPS and GNSS. And I don't need to go through this. You'll all be aware of the various systems that are now available to us. But one of the interesting develops, certainly down in Australia, across Asia, is the development of the Japanese QZSS system, which is a number of satellites which will augment the GPS system. But they're not in orbits, they're in orbits that circulate over Japan, but in putting them all in orbits like that, they actually loop down across Australia. 3 satellites are planned. The first satellite has gone up. And one of the interesting features with these satellites is they form part of the GPS network, so they have the same signal structure and so on, but they actually broadcast corrections down to the receivers. And the intention is with the system that it should enable real-time positioning at the sub-decimeter level, possibly down to the 1 to 2 centimetre level. Now, this is going to present some interesting opportunities for us down in Australia and New Zealand, because if you look probably out 5 years from now, when the 4 main systems are up and operational, and the additional satellites that Japan are putting up, it's going to give a huge number of satellites that will be available to be used by users of GNSS down in the Australia-New Zealand area. So this diagram shows, I think it was planned for about 2020, the number of satellites that should be available for making GNSS measurements. So the lower blue area over, interestingly, across North America will be, so this is satellites that will be available at any point in time in the order of 30 odd, but over Asia and perhaps down in New Zealand, we might be having access to anything up to 40 or so satellites at any point in time. And as I say, some of these satellites are going to be giving some interesting signals and corrections. So I think it's going to, it is presenting some interesting opportunities. We're working very closely with some researchers in Australia, which are looking at how we can take advantage of all these signals that are going to be available to us. So turning to New Zealand, our national cause network, which we call positions. This diagram is just a little bit out of date. We have a national network of 35 stations. It is a network which is run jointly with GNS Science in New Zealand. GNS Science, I guess, is equivalent organisation to US Geological Survey. They have an interest in monitoring crustal dynamics from a hazards perspective. We have an interest in the network for monitoring our datum. So the prime reason for developing this network was to monitor our datum so that we could accommodate those effects of plate tectonics and so on. One of the key features for this network is the fact that we want stations that are stable. So each of these stations in this fundamental network are all located on solid rock, similar to the picture up on the right-hand side. A number of these stations contribute to a number of, to the IGS, a number of international projects. So the 4 stations circled in red there, stations contributing to the IGS. We have 3 additional stations in Antarctica that we're responsible for, and that contributes to the PolNet program. We've recently got a VLBI station up and running up in Auckland, the yellow circle. And all the other data from all the other stations is freely available, open to anyone who wants it, both as RINEX files and also as 1 second string data. In addition to that network, there are a number of other networks in New Zealand. GNS Science have a more dense network, the reef stations here, which are focused on monitoring along the shear belt of New Zealand and through the Taupo volcanic zone. Another 80 stations in addition to our network. And there are plans to extend that network into the South Island. The blue stations there and a couple of yellow stations show some additional stations that the private sector are running. And they're really adding stations to enhance our network so they can provide real-time networks to users of GNSS for accurate positioning. So just to look at some of the results, and again, these will be, I'm sure, quite familiar to you. Because we live across the plate boundary, if we look at the vectors of movement, it's not showing as a block movement, but certainly you can see that differential movement as you move across the plate boundary. Typical of one of the stations here in Wellington, where I come from, a typical record through time showing the slowed movement due to the plate tectonics. A number of stations, or a number of interesting features, a number of stations up along the east coast of the North Island show these slow slip events. A lot of work's been done, was by John Bevan, who's sadly not with us now, but John Bevan was studying these slow earthquake events. So these are events which are occurring on the plate boundary, probably at a depth of 100 or so kilometres, representing these slow slip events in the order of 5 to 6 centimetres at the Earth's surface. And again, from a practical perspective, from the aspect of LINS and managing a spatial framework, we have to find some way of accommodating this into our survey network to maintain that accuracy of 5 centimetres that we're looking for. Over the last, well, I guess certainly the time that this network's been up and running, we've also had a number of large earthquakes. This is the effect of a large earthquake down in Fiordland, down in 2009. It was a magnitude, do I have it on there? I think it was about a magnitude 8.4 earthquake. It was the third largest earthquake in the world in 2009, but very deep at 200 kilometres. So it didn't create much damage. It's also an area where there are not so many people. But essentially the whole bottom half of the North Island, our cause network showed the effects of the movements of that earthquake, and this is one of the stations close to the epicentre. And again, from an operational perspective, from LINS's perspective, again, we have to apply a correction to our whole geodetic framework to accommodate the effects of these sorts of events. And then more recently, back in 2010, we had the first of a sequence of earthquakes around Canterbury, close to Christchurch. This was the first event, resulted in a surface rupture of several metres. So you can see the hedge line up there with the offset in the trees, the same with the road here. And again, quite clearly was recorded by our cause network. Now, I'll spend more time talking about this and some of the issues with this, but across New Zealand, our cadastral network, so in New Zealand we have our cadastral boundaries are defined by survey, and those surveys are tied into our geodetic framework. So all our cadastral property boundaries, the corners of your properties, essentially have geodetic coordinates on them. And again, we're trying to maintain that accuracy of about plus or minus 5 centimetres, which is the size of your peg. So when you have this sort of effect here, all those property boundaries move, and one of the issues we have is that we have to re-coordinate them. So if that was a property boundary along that hedgerow there, here before the earthquake, had a straight property boundary. Now it's got an offset in it, and we have to find some way of accommodating that. From a computational perspective, it starts becoming very complex, because if we want to adjust our geodetic framework to take out the effects of these earthquakes, we're talking about adjusting tens of thousands of points. As soon as you bring in the cadastral framework, we're now talking about adjusting in the case of just Christchurch alone, 1.25 million points. So computationally, it starts getting a lot more complicated, and the problems start getting to be a little bit more interesting. But I'll talk about that shortly. Just recently, we had a series of earthquakes to the north of the North Island, down in here. Also affected Wellington. This was just a few weeks before we came away. Again, the Geodetic Framework very quickly was used to look at what movements had occurred. It caused a little bit of damage in Wellington, shut down our building for 2 days while it was checked out. But again, the Geodetic Framework playing an important role to determine what mechanisms were occurring. I'm going to turn just very quickly to our vertical network in New Zealand, because not only do we have a cause network, we also have interest in maintaining a vertical network, principally used by engineers and so on, surveyors. In New Zealand, we don't have one national sea level vertical network like most countries, including the US. We have a number of networks shown by the different colours on the left, and each one of those networks is tied to a separate tide gauge. And the reason for that is that across New Zealand, there is a difference in level of sea level of about 0.5 metre due to tidal currents and densities in the water. And if you start trying to adjust it together, you start throwing in all kinds of distortions and errors due to the difference in sea level. So we've always resisted adjusting our network completely together to have a single vertical datum. But of course now most countries are moving to vertical datums that are not even based on sea level, they're based on the ellipsoid, and using geoid models to go from ellipsoidal heights down to heights which are approximately the same as sea level. So in New Zealand several years ago, we took all the gravity observations that we could get our hands on, several million points, and developed a geoid model which has an accuracy of about 8 to 10 centimetres, which is not really good enough for most engineers. Most engineers that are putting in drainage want heights that are good to about 2 to 3 centimetres. So we put up a proposal a year or so ago to try and improve the accuracy of our geoid model. And we were aiming for an accuracy of about 3 centimetres. Looked at how we could do it, and it was impractical to go out and carry out more land-based observations. So we put up a proposal to fly airborne gravity across New Zealand, and recently have had that proposal accepted. So we did a test case in across Canterbury, and that showed us that we could get repeatability in our airborne gravity measurements of about 2 milligauss, and have now come up with a proposal to fly gravity across New Zealand. And this project has just started, so just as of about 2 weeks ago, we've started flying it across New Zealand. The program will go for about 2 years, but at the end of that program, we will have flown airborne gravity across New Zealand, and hope we should end up with a new national vertical datum based on the ellipsoid and using the geoid to be able to determine heights with an accuracy of about 2 to 3 centimetres in terms of the geoid using GNSS. That's just sort of some of the summary of what I've been talking about. Another new development in New Zealand, again, some of these technologies for a small country like New Zealand are very expensive. We've started making some VLBI measurements. We were lucky enough to be able to work with a university in Auckland that had a proposal up to put up a radio telescope to look at radio astronomy, because these telescopes can also be used for making VLBI measurements. And so by having that dual cause, we're able to make a much stronger case to get funding for the telescope. So 12-metre telescope has now been up and running for several years, co-located with GPS, and we've started making measurements, certainly with our colleagues in Australia, trying to build up our skills in the use of VLBI and making VLBI measurements. We, in another location in New Zealand, there's an old telecommunications telescope, a 30-metre telescope, which is now not being used. And our next step is to try and see if we can get access to the use of this telescope, so we can have 2 stations running in New Zealand to be able to make VLBI measurements into the future. So I think from a geodetic perspective, there's some really interesting trends coming up. And if we start looking at 10 years and start looking at what is the role of geodetic, national geodetic organisations in countries, there's some really interesting things that are going to really start hitting us into the future that we're going to have to think about. And it's quite clear that within 5 years, GNSS modernisation is going to have a really significant impact on all classes of positioning. And I think when you have that ability to get real-time positioning or absolute positioning down at the sub-decimeter level using your cell phone, and I believe it will come, then it's going to present some real challenges for geodetic organisations such as LINS and the National Geodetic Survey here in the US. There's no doubt that around the world, geodetic frameworks are being regarded as national infrastructure. There's a real push to the use of location-based information. You must have a strong geodetic framework to be able to do that. So in New Zealand, for example, our department, which used to sit under an area which was responsible for the environment, has now been put under a group of government departments responsible for infrastructure, which includes things like electrical grids, transport systems, and so on. And I think that's really interesting that even at government level, they see the geodetic framework as being an infrastructure. And it's often referred to as infrastructure for infrastructure. You have to have a geodetic framework before you can have a roading network. Otherwise, how on earth do you build anything? I think there's some really interesting developments, particularly around augmented reality, where you're trying to integrate the real world with the physical world in devices such as iPads, so that you can take your iPad out and with the video capabilities, look at bringing the digital world in, such as underground pipes, all together in one device. And again, to do that, you have to have your device and all your infrastructure in the same framework. And again, the geodetic infrastructure enables that to happen. So there's going to be some real challenges on how we do that going forward into the future to maintain that spatial accuracy, certainly down at the decimeter level. And I think the real challenge for survey networks is that if you look at where national geodetic sort of organisations sit, we sit up in the top right-hand corner there. If we look at positioning as an infrastructure, and we look at increasing accuracy up along the left-hand axis and increasing reliability, we see that for the aviation industry, they're not so interested in really high accuracy, but they must have a system which is completely reliable. You can't have some kind of navigation system based on GNSS failing just as a jet's coming into land. But they don't need that centimetre accuracy. If you look at the surveying community, they want relatively high accuracy, but if the whole system goes down, well, it's going to be annoying, but it won't really bother them too much. But they are asking for greater accuracy, as is the aviation industry. And the mass market, what I call the Google market, sit down with your cell phones and so on, and there with your Google phone trying to interface with Google Maps and so on, really if you've got an accuracy of a few metres, that's fine, and if the whole system goes down, well, people are going to be annoyed, but they're not going to be too worried about it. So there's a real split between what national survey organisations will provide for. So we provide for the high accuracy, pretty good reliability area up the top. Google and so on provide the area down the bottom, and we can see the line splitting it. But there's no doubt that in the future, there's going to be a huge increase in the requirements by what I call the mass market. There's going to be applications that we haven't even thought about on our cell phones, where people do start wanting a much higher accuracy and increasing reliability. And the challenge for mapping organisations such as LINS and geodetic organisations is to what extent that we actually start supporting that mass market. And already we're looking at phone apps to enable cell phones to be able to integrate with our databases so that the deformation model that I talked about in our datum can be used to update spatial coordinates in cell phone type apps. So I think you're going to see national mapping agencies having to look at this mass market and how we support it. And I think some of the challenges going forward will be some of these challenges here, and I'll just have to put on my glasses. I can read it from there. I think for the mass market, they're not going to be concerned about earthquakes and what the impact is on coordinates and databases and so on. So we need to have a system which is invisible to users. In the same way that you read your watch, you just expect it to be accurate. You're not concerned about how time is managed and everything is kept in sync worldwide. It just happens. And there's a lot of complexity there that we're going to have to remove through apps where spatial reference frames and cell phones and different apps that are being used just automatically get updated and people don't even see it happening. Maintaining that accuracy is going to be crucial, and I've talked about sort of some of the earthquakes. How do you maintain in countries like New Zealand and other countries? Australia, even though it moves as a block, is looking at putting in a semi-dynamic datum or a dynamic datum. How do you maintain that accuracy as different events happen? We're beginning to look at a new national datum in New Zealand. Our national datum is 13 or 14 years old. We believe that by 2020 we're going to need a new national datum, which will probably be fully dynamic. So coordinates will change all the time. It probably won't be a coordinate that's specific to New Zealand. We'll just adopt the ITRF at the date and then provide a more accurate deformation model as part of it. Real-time coordinates is going to be a real challenge for us as they change. As I said, now the coordinates in our databases are coordinates as of the 1st of January 2000, but people want real-time accurate coordinates. For a national agency like LINZ, we want to be leaders and not followers in the whole survey space because there's going to be new technologies coming along, and we need to be in a position to be able to tell people what those technologies are and how to use them. To embrace new technologies, and I'll cover that in the next part of this presentation in Canterbury, because some of the tools for the Geodesist are changing. Remote sensing in particular is being used much more in geodesy now than it ever was. And the final point down there was to the extent that we need to support that mass market is going to be a real challenge for us, and how we do that is something that we are now beginning to work through. And as I say, looking at providing apps that can be downloaded onto cell phones so people can actually integrate and use some of the features within our geodetic system. So I wanted to swap tack a little bit now and talk a little bit about the Christchurch earthquakes and how we've used the geodetic observations to monitor some of the movements and some of the challenges that we're facing down in Canterbury. So I've covered some of this here. So as I said, in New Zealand we have a geodetic framework which is accurate to 5 centimetres. The cadastre is tied to that framework, so we have geodetic coordinates on all our property boundaries. And as a result of the Canterbury earthquakes, what is the impact and how are we going to go about trying to fix up that whole spatial infrastructure around Canterbury? The photograph here was a photograph that was taken a few minutes after the Canterbury earthquake, and it's actually not fires burning there, but that was just dust that was brought up as a result of the actual shaking and earthquake. So the first of a series of earthquakes occurred in Canterbury on the 4th of September 2010. It was a magnitude 7.1 earthquake, so in terms of large earthquakes, it was not that large, but it occurred at a depth of 10 kilometres, so it was very shallow. And it resulted in a fault rupture. The Greendale Fault is indicated in the red over on the centre left-hand side. Christchurch, with a population of about 360,000 people, with some about 50, well not quite 50, about 30 or 40 kilometres out to the east of the actual fault rupture. And as I showed before in the photograph, resulted in an obvious break, not only the horizontal movement, which was quite evident up in the top photos, but also a substantial amount of vertical movement. And you can see by the ponding on this ditch here that there was subsidence on the one side of the fault. One of the biggest sources of damage in Christchurch was not the actual, it was a result of the shaking, but was actually liquefaction. So there was a huge amount of liquefaction around Christchurch, basically the ground turning to jelly. That resulted in a lot of spreading. And that was focused around some of the rivers and stream courses around Christchurch. But a good example here of just lateral spreading as the ground liquefied, houses were pulled apart by a metre or so through the area there, and a lot of soil was ejected, caused a lot of damage. I talked a little bit before about greater use of remote sensing now for looking at the effects of some of these events. So here was a differential INSAR piece of work that was done by GNSS Science. Clearly shows the area of effect of the earthquake. So because it was relatively shallow, the movements were restricted to quite a small area, certainly outside of 80 to 100 kilometres, very little movement. Unlike that earlier earthquake in 2009 in Fiordland I talked about, where it affected the bottom half of the South Island because it was much deeper and also quite a lot larger. So the actual extent of movement was relatively small. And immediately following the earthquake, went into the field, carried out some surveys of our existing geodetic framework. You can see the results of the movement there, the blue vectors. So movements in the order of up to 2.5 metres across the Canterbury Plains and across that fault rupture. Looking at more detail in Canterbury, because that's where most of the actual damage occurred, this diagram here shows a network that we resurveyed in Canterbury. The pink areas there indicate those areas where we had the liquefaction. And if you look at it, the actual horizontal and vertical movements, which we're nowhere near as great as out by the fault rupture, we're relatively consistent, that apart from one or two sites where you see some outliers, and where you see those larger movements, they occurred where we had marks which were in these areas which had liquefied. So from a survey perspective and looking at how we could readjust the cadastre, it looked relatively simple, that we could apply some corrections to cadastral boundaries, but perhaps where the liquefaction was, we would have to go and do a lot more surveying to try and get a better handle on some of these more movements that were a little bit abnormal. This project was done with GNSS Science, and they were able to take some of the early observations, the blue being the observed observations on both the horizontal on the left and the vertical movements on the right. We're able to take those observations, model the fault displacements, which showed as a complex series of fault displacements on the left, and the red indicate the modelled as against the blue displacement. So we're able to model quite well using the geodetic observations the actual results of the earthquake. And so very quickly we came up with a plan to look at how we were going to readjust the network in terms of the marks affected and what we were going to have to do. This is looking at sort of rings or circles out beyond the epicenter of the earthquake, and probably the totals along the bottom is the one to focus on. So in terms of marks affected, there's something like 6,000 geodetic marks that were now out of position and we were going to have to be readjusted. Cadastral marks, which are other survey marks that cadastral surveyors also tie into, something in the order of nearly 90,000, but there were 1.25 million cadastral boundary marks that were now all out of position, and we were going to have to look at going in and readjusting them. Now, it's totally impractical to go in and resurvey this number of marks, so you have to come up with some kind of model so that you can correct all the coordinates for it. And so using this network, we came up with a model, and probably this next diagram is the one to show. By being able to model out the displacements due to the earthquake, we were able, or going to be able, to correct most of the displacement. So the very small vectors show the residuals that would be left after modelling out the displacements. Across most of the area, we could do a pretty good job, but there were some outliers, as I said, in Christchurch where the ground had liquefied, and being close to the fault where the fault model didn't work too well. So we were left on working on a model to look at the effects of the earthquake, looking at how we could adjust it, and by being able to adjust out these movements, we thought we'd be able to correct about 90% of our geodetic and cadastral marks relatively simply and quite easily, but also recognising there would be some areas where we would have to go back and do some more surveying, notably close to the fault and these areas that were liquefied. So just looking again at the areas of liquefaction here, the pink areas were the areas where we thought we'd have to go back and do some additional surveying. But then everything turned to custard a little bit in 2011, when on the 22nd of February there was another earthquake which occurred much closer to Christchurch. And the second earthquake occurred here where the red star is. It was a magnitude 6.3, but it was even at a much shallower depth, only 5 kilometres. And it resulted in some much more severe shaking, in some cases with some strong motion instruments that were located around Christchurch, up to 4G. And it resulted in much more severe damage to Christchurch, a lot of building collapses, the loss of nearly 200 lives, and much more severe liquefaction. So huge amounts of liquefaction, number of major building collapses. And right now in Christchurch, I think something like 2,000 buildings have been pulled down in the central business area. So I think Chuck's been to Christchurch. If you go there now, big areas of open space, something in the order of 5,000 houses are now going to be moved away because of the ground damage. And one of the roles of LINZ is to manage that whole process of taking the housing away. And the rebuild is just beginning to start. A huge amount of liquefaction material brought up, and just as an interesting side effect, which reminds me with the troubles we've been having around here with the recent flooding. An interesting student called Sam Johnson had this idea that he wanted to get all the students in Canterbury to be involved in the clean-up around Canterbury. So he went to Civil Defence and said, well, we've got all these students from the university. We want to help. What can we do? Local Civil Defence said, don't bother us, we're too busy. So Sam decided that he would get together using social media and galvanised an army known as the Student Army in Christchurch. And they went out and they just started going around the properties and digging out houses, digging out all the silt that had been brought up, and did a huge amount of really great stuff around Canterbury with his Student Army. And that Student Army has now been formalised in the Canterbury University and in other universities around New Zealand, so that whenever there are events like this, or flooding, where people need help, they can just get on the ground with their spades and shovels and just go from house to house and help people. So an interesting example of what you can do if you've got someone with a bit of foresight, and you just get on and do it. You don't have to wait to be asked, you just do it. So the big problem this time was that the areas of liquefaction across Christchurch were far more extensive. Slightly different diagram, but the areas of red where there was some severe liquefaction, and the yellow areas where it was low to moderate. So much more extensive areas of liquefaction. And as I say, there's quite extensive areas of Christchurch now where basically all the housing has been removed because the damage was so severe. Those areas will probably just be turned into parks, and huge building going on, particularly out towards the west of Christchurch where the damage wasn't so great. So again, I'll skip through these pretty quickly. So again, differential INSAR was used to get a picture of what was going on. Survey was carried out of our Geodetic Framework, and again, the fault model determined a very different mechanism to the earlier earthquake. There was a lot of debate whether the second earthquake was on the same fault structure as the first earthquake. Appears to have been on quite a different structure. The movements were quite different. There was uplift to the east of the fault as against subsidence on the earlier fault, and again, quite substantial areas of vertical movement. So again, looking in a little bit more detail, when you started doing a detailed survey of the area, there was a lot more randomness on the movement. And again, that was principally because of the extensive areas of liquefaction, both in the horizontal and the vertical. So this time around, we tried to see if we could come up with a model so that we could go in and correct the geodetic framework for the effects of these earthquakes. And really, we decided quite early on, this diagram shows the residuals that would be left if we try to apply some uniform model. Really, it was clear that that wasn't going to work. So now, as a result of that, a lot more surveying is going to have to go into Canterbury as the rebuild starts and as we start putting back together the spatial framework which will enable property boundaries to be re-established. Because in central Christchurch, in a lot of these areas, if you bulldoze everything away, you take out any kind of physical evidence of where the boundaries were. But people want to re-establish properties and business, they need to know where their boundaries are. So a lot more surveying and work going on down there right now. So as I said, as a result of this second earthquake, we think only probably about 50% of the survey and cadastral marks can be put back by applying some kind of model. I'm going to finish very quickly just by showing a couple more slides and some of the other techniques that are being used down there to look at some of the movements that have occurred. And LiDAR in particular has been playing quite a big role. A lot of LiDAR flown, fortunately, just before the series of earthquakes and luckily just after the first one. This is a diagram looking at LiDAR taken before the Christchurch event and then after it. And what the diagram is showing you is horizontal displacements across Christchurch. And that's all that the diagram is showing, the little vectors there. We're also showing on there the blue areas of compression and the red areas of extension. And there's a very striking feature that runs through the middle of the diagram, and that feature actually happens to line up with the Avon River. So what's been happening is that along the banks of the Avon River, with all the shaking, there's been extension, spreading, and the spreading has been going into the bed of the river, and that's shown by the blue there. And of course, on the bed of the river, that extension has got to go somewhere, so the actual river beds have been shortening up, which in itself has caused a problem because Christchurch is a very low-lying area, and there was some concern about flooding, particularly if the waterways were actually getting smaller. So interesting features to show some of the effects of the liquefaction that had occurred there. And then there's been quite an extensive program of reflying quite regularly LiDAR across the country. And again, the blue shows areas where the ground is, if you like, has got less, and the red where the ground has got greater. So this is looking at the buildings. The blue there are buildings that have collapsed or have been completely removed, and this was a shot taken about a year ago. So you can see that the red buildings are beginning to be rebuilt. So LiDAR is proving to be a huge tool down in Canterbury as this rebuild goes on. A lot of work to be done. It's about a $20 billion rebuild, which for New Zealand is a pretty massive undertaking. But interestingly, a lot of the insurance is funding a lot of this. Government's having to put in, I think, about $8 billion. But most of the insurance was reinsured offshore. So it's actually new money coming into New Zealand. And it's causing a huge building boom in New Zealand right now. And of course, every builder is rushing down to Christchurch to build, well, I think something in the order of maybe well in excess of 5,000 houses, plus the huge rebuild of the commercial properties within Christchurch itself. They're going to limit the buildings, I think, to 4 stories only. But the rebuild is going on, and whether there'll be another event in Christchurch, well, I guess we don't know. There's always been that concern, particularly with the sequence of earthquakes. When do you start the rebuild? How long do you hold off before you start? But really, right now, the rebuild is getting underway. Strings. Speckled areas are trees. So trees have grown, so they've got highs. So they tend to be where the trees are. So LiDAR is really good for measuring tree growth as well. So that's really it. And what I wanted to do was to try and give, I know that UNAVCO, you're focused on the science using Geodesist, GNSS, but there's the flip side, that it does use of GNSS and spatial frameworks, geodetic networks, plays a very important role from just maintaining that spatial framework, so you can bring together all these different diverse data sets to do the many things that people do. And a lot of those sorts of things are now being done in people's cell phones. And what you do, looking at a scientific aspect, does have a very real application. And those applications are not just going to be applications that cadastral surveyors and engineers have traditionally used. But I think you're going to find that everyone in this room is going to be using tools that are going to be using aspects of the Geodetic Framework on things that we haven't even thought of right now. And it always amazes me, some of the applications that people come up with. We typically think of our car navigation systems as is a map, but it's got to have some spatial component to it. But there's many, many more things that are just on the horizon, I think. And these whole frameworks are an important part of that. So happy to take any questions in the last 5 or 10 minutes.
Great talk. That was really interesting. How many of the stations do you operate in lands? That's 30, 40? You have the CORS network?
35 we have responsibility for. With GNS, it's very much a shared network, but we fund that network, and then 3 in Antarctica, plus a couple on
then there's the 80 from the GNS.
Yeah, I think the network is getting close to 100 now. It might even be over 100.
So my question is, right now, are all of those stations GPS-only stations, or are most of them GNSS stations?
No, our network we upgraded probably a year or so ago, so they're all definitely GNSS. The GNS stations, the ones that GNS are putting in, the new ones are using net, what's the latest, Trimble net R5, is it?
R9.
R9. Some of their other stations are planning to upgrade as soon as they can, but their priority is getting the new stations in. I should also point out that our network, all those stations stream data, and New Zealand government has a policy of any information we collect is provided free of charge to anyone. So we don't make any money off our network. And GNS Science, with their additional stations, are also going to move to that model. So they'll all be real-time streaming data free of charge to anyone who wants them, which means companies like Trimble and Leica can come in, put in a few extra stations, and then have a networked type solution. They can make money from it, so they're getting the benefit of our stations. The benefit we get is that if we have an event like Canterbury, we've got an arrangement that they'll just provide all that information to us in the rebuild. So in Canterbury, we only had one of our stations that actually recorded that event, but there were about 3 or 4 private stations running, and although they're on buildings, and buildings shake around and don't know how reliable the results are, we've had access to all that data, and that's now being used in the rebuild. So really, really good working relationship between the private, the public, and I guess the science sector in New Zealand, and we're small enough to be able to do that.
I have one other question that's sort of a science question, which is when you did the inversions for the co-seismic displacements, did you just use geodetic information, or did you also use strong motion and teleseismic information?
That was where it was done by John Bevan most of that week. I think it was just the geodetic observations. I know they did have some strong motion information. Obviously, they would have been comparing it with the seismic work as well, but I think the results I presented here were just purely the geodetic inversions.
So I have just a legal question. If you have that nice hedge that goes through and it has this nice huge offset, and your boundary was defined by 4 points on the ground, do you own the line between those points, or do you still own that offset?
It's a very good question, Chuck. We're not really quite sure. There's no legal precedent for this. Now, so normally on a property, if it's got 4 pegs, the boundary is the straight line between the marks. So in the case of the hedge, it would be the straight line. Let's say it was the end of the end of their hedgerow. If there was some value associated with that hedgerow, let's say the trees had some value, that would mean that half the trees would now actually be on your property, on your neighbour's property, and he will have the benefit of those trees suddenly appearing on his property. So as a result of this here, it's really done on a case-by-case basis. A lot of small lots, it is the straight line between the boundaries, and if you're not across that fault break, the movements on a quarter-acre lot are really not going to make the relative movements are not going to make much difference. But on the case of the hedgerow, if that was the case, then what would happen? There would have to be a new survey done where additional pegs would be placed, and it would actually be the offset. Now, the interesting thing is with the liquefaction, this has been raised around the streams. Essentially, if you've got spreading, those people that have got properties by the streams, their properties have actually got bigger. But the council who owns the watercourse, their property has got smaller. Now, then we might think, well, that's all right, just bad luck. But there's a real concern about the storm water hazard now. If they want to start dredging out and broadening the watercourse, do they have the right to actually claim back to where their boundaries would have been before the earthquake? And that's an interesting question that's being considered right now. So it's not simple.
And who gets to make that decision?
Well, it would go to a court of law, and there's already been a number of cases taken. And as I say, it's really being fought on a case-by-case basis. Most of the time, you can get agreement, but it's an interesting one. Yeah.
Okay, I actually have two questions. One is that figure you have up right now. It's been bothering me. What is that red building? It doesn't look like a rubble pile.
No, so that's a new building that's been built.
Oh, new one.
So,
Okay.
so it's a new one that's gone up.
Okay, and the other one is, can you give us an idea of the local crustal structure, seismic hazards, faults mapped in the area?
For around Christchurch.
Yeah.
And so the seismic hazard in Christchurch was regarded as extremely low because it's a long. Oops. Sure, I can go back quickly. If I can go right back. Come back. No, I'm going to go right back. It's a quicker way of doing this, I know, but sorry. There. Go right back up to. It's.
So there weren't that many mapped faults then.
Right there. Okay. So I guess the seismic hazard, the highest seismic hazard in New Zealand is through the east of the North Island, running down along the shear belt, through Wellington, through Canterbury where all the faults are, and then down along the Alpine Fault. So Christchurch, which is quite a long way away from the plate boundary, was always regarded as a very low seismic risk. So consequently, a lot of the buildings in Christchurch have, from an earthquake engineering perspective, hadn't been looked at. There was a lot of brick buildings. In Wellington, for example, which is a very high seismic risk, there are very, what would you call them, severe or very strong earthquake building codes, just because of the risks. So a lot of the damage in Christchurch was really because of the building standards. The area there, there's a lot of outwash gravels from the Southern Alps. So there's several hundred metres, I think, of probably more than that, of gravels. So these faults that have moved, they're obviously there, but no one knew that they were there. You'd have to use some kind of seismic.
There's no background microseismicity there?
Extremely low. So it came completely out of the blue. It's interesting that when the earthquake occurred, a lot of people in Christchurch thought, goodness me, if we're getting this sort of shaking in Christchurch, what's the shaking in Wellington being like? The assumption was that the earthquake was probably somewhere north of Wellington. They didn't realise it was actually on their own doorstep. So now, as the rebuild starts, then the building standards have gone right up. So the piling, for example, is now going to go right through the gravels and find something more substantial. So no one ever expected there to be a large earthquake in Canterbury.
Thanks.
I guess it shows you that a place like New Zealand could happen anywhere. Yep, I think so. So in terms of what we're doing, so we're in the process now of doing a major readjustment of particularly all the South Island, all our geodetic control, all the cadastral boundaries, which should fix up the effects of these large earthquakes. In fact, it's on hold just a little bit while we also map in the effects of these earthquakes just in the last week or so. When that adjustment runs, then we'll update all of the coordinates for all the boundaries, which will go into our survey and title business, which is used by cadastral surveyors. The problem we have is that we've got to get the adjustment down to run over a weekend before we can do that update, because we can't afford to take our whole survey and title business down. So that's the basis of property transactions and so on. And we've almost got it to run over a weekend, but it's been a bit of a challenge. Just a side problem that you're under time constraints for doing some of these things. When you've got an operational system that people are using, you can't just sort of do the niceties and take your time. It's got to be done in a way which minimises the impact on users of the system.
Okay, well, join me in thanking Graeme one more time.
Good. That's all right. My pleasure. Like Japan.